So what we're going to do is use Gaia to find like any deviation from normal star trajectory. So from a gravitational lensing from a foreground compact object that you can find. So the outline is we're going to do a brief review of what gravitational lensing, hopefully everyone knows. And I'll talk a little bit about how Gaia acquires its astrometry. Then the work that we've done is we've developed a analysis pipeline, so that way that you can inject whichever lens you want under like any kind of model you want. So for the purpose we did the first one is astrophysical black holes, so just the black holes that form usually from stellar evolution. And then we also did a search for compact dark matter. So for example, like primordial black hole. And in case I run out of time, I'm gonna just spoil the result now for you guys. So this analysis pipeline, what we did is this whole framework. You can have like a flexible and faithful catalog of so this will be by flexible. I mean is you can do whichever model you want. So you can instead of black hole you can add neutron stars or you can add white dwarfs, right? And for dark matter, what we did is we do a NFW profile, but you can also consider different profiles that you want to add. And then faithful is what we try to mimic what the actual Gaia data release score would look like. And so you can this has some like tangible like accountability of what you would possibly see in 2025 when this comes out. And for our mock search, what we see is like we can project that the Gaia can will probably see around 4 of those astrophysical black holes at 5 sigma levels. And for the compact dark matter, we have the leading Gaia will provide like leading constraint in the mass range of 1 to 1,000 solar mass, and then with the dark matter's substructure fraction to around 1%. So this is the summary of what I'm going to talk about.
I have one point
Yes.
of extreme pedantry.
Okay.
Which is that Gaia is a spacecraft, not a satellite.
Okay. Again, we can
I
work
warned
with,
you it was extreme pedantry.
we can work with different terminologies, but yes.
Does it have a satellite also?
Not really, because it's at
Oh,
L,
it's some
'cause it's at
L something, so it's not a
Yeah.
satellite.
Yeah,
L2, it's still orbiting the Earth.
well, in a kinematic sense, but not in a gravitational sense.
Okay. So,
Hey, I have one role. I have one role in here, and I'm living up to that
But
role.
that's good, we learned something.
so a quick review of gravitational lensing. So, say we are here, right? This is our eyes, and there is a.
Sorry, this 4 black holes, it's the future when it gets applied. or
Yeah,
what?
yeah. So yeah,
What are you waiting for?
because this is 2035.
When there is much more data.
So they have some data now, but the format isn't what we want. The format, I'll get to that later.
Oh, okay.
Right.
So you have not started processing the real stuff.
No, we just made a mock data that we think would look like in this format. Yeah.
Okay.
So this is our eyes, and then there's a distant star here, and then we have let's say a black hole in between, right? Then general relativity tells us that this black hole can bend the light coming out from at a background, but you see what I mean? Yeah.
It does bending at funny places though.
There's a lot of
here. Apologize for the chalk.
At least it enriches us.
Chalk is hard to draw with, so
it's a
More
tough
serious problem
audience.
than that.
yes. Please do, yes.
There's a
So-
repulsive gravity on one side.
Anyhow, yeah. So it spans like exactly here. So you can assume that it's straight line and straight line. Okay, and then so what it does is it creates two images here. So one of the image would be here, and then the second image would be here. Imagine like
That was easy.
I'm pretty sure us like physicists we have good imagination, so just imagine it. Straight lines. Good.
He's not the one to be intimidated.
So here this is some impact parameter v, and then you have the distance to the lens and distance to source. Okay, so what general relativity tells us is for this event there is a characteristic scale. So the characteristic scale is when this impact parameter is 0. Then when you instead of seeing two images, you see like a ring, right? And then that the radius of the ring is given by the Einstein radius, and so this is given by this formula here, and in the case where let's say this distance to source is larger, much larger than distance to lens, then if you want to like learn the parametric dependence on this Einstein radius, then this is roughly 2.85 milliarc second, and then the dependence is for a 1 solar mass lens at 1 kiloparsec. So this is a tiny angle for any like galactic source for lensing. So sorry. So what we traditionally do to detect this effect is you can say, okay, so the separation is roughly given by this scale, right? So most of our telescopes has resolution that's worse than this, so we don't really resolve both images. So what we see is the light centroid of both sources, so it'll be somewhere, let's say somewhere here, right? So this is like you have a telescope collecting those lights, and then the combined effect is you see some star here. Okay. So because we're physicists, we like to a-dimensionalize things, right? So to define a dimensionless this is what we're going to use for this. This will be E over. So this how large is this impact parameter compared to the Einstein radius? Any questions so far?
You assume that usually ds is much bigger than dl, right?
Oh, no, this is just for learning the parametric dependence, but the actual calculations, we're all using like the full.
Generically, there's no like, they could be similar, they could be
Yeah.
bigger. Okay.
Yeah, so in terms of like, if you look at this formula, right? So if the lens is like at the same distance to it, then like you can, the intuitive guess would be there'll be no effect, right? So you can see it from the panels here. Yeah.
In that, in your expression, the DL in your scaling expression, you could just call D, because this distance ratio, distance difference over two distances has units of 1 over distance. So there's just some 1 over distance
some 1
over
over
there. It
distance.
isn't necessarily
Yeah, some
distance of the lens.
order 1 like order 1 like constant that depends on the difference between them. Yeah. And so we did define dimensionless impact parameter, right? And then the effects are there's a small angular deflection here. So you can call it like delta theta. Then this angular deflection is parametrically, it's a simple function of this impact parameter u. And if we look at the two extreme cases, right? So when u is much less than 1, then this scales as 1 over u. Then the u is much larger than 1.
Wait, I
Isn't
think
it
you wrote
opposite?
it backwards.
U, sorry, yes. And in the other case, it is 1 over u. And so additional from this angular deflection, there's also another effect, which is this source will be brightened. So by the lensing effect, so it's like think of it like a concave or convex, right? But it's like a lens that can collect more light, so the star would appear brighter, right? So this the brightness or magnification is also another function of this. U and the parametric dependence is 1 over u here. So looking for this magnification is what people have historically done to try to detect any compact dark matter in the galaxy.
Sorry, what did you write for large u?
What you're writing wrong.
For large u, it should be 1,
And it is 1.
Sorry.
not for small u, for large u, right? I'm just reading your
Yeah,
formula.
that's right. You're right.
Yes, I was right. Yes.
As 1, sir. No.
What is
U
this? It should
big.
be 1.
Yeah, it's 1 leader, but there's the u to the u squared term is, okay, so I should say this is 1 plus. This should be 1 plus u to the 4.
1 plus. Okay.
Yeah, so this is like the additional brightening. Yes.
Then write 1 plus, otherwise we will rebel.
Yes. Okay. Yes. Do you have a question?
No.
Oh, okay. Okay, so this is what people historically do. So in the 90s, there's different projects. So there's a French collaboration, and then some Australian, and then also like. So these are all. They have like the results are up there. We'll talk about it later. So these are the surveys that basically look at the Magellanic Cloud and galactic center. So they have like the most background stars to look for, and then they're detecting some see if there's brightness change, and they translate that into constraints on how many dark matters are in.
But did they also detect something?
So I believe that module detect 1. OGO has 3 or 4, but they're all consistent with just regular stuff.
So like how many, do they look at specific objects to see if they detect the lensing effect, or do they just do a survey over a patch? And
Yeah, they just do a survey over a patch of the sky. So
okay, so how large of an area did they?
it's Magellanic.
Okay, so it was the full Magellanic Cloud.
Yeah, so
Okay.
it wasn't like, it's not a huge patch compared to like the full sky.
Yeah. Yeah.
Right, yeah, because like for brightness you want like large exposure times to get good accuracy. So the difference between the angular deflection and brightness is Gaia is a full sky survey. So there's more stars to look for this effect compared to just staring at a small patch of stars.
Sorry, what exactly did they detect?
So they just basically seeing if there is any brightness effect.
Well,
right?
you said they detected something.
Yeah,
What
they did.
exactly did they detect?
Okay, so this is still running today. They detect a lot of exoplanets. So exoplanet also cause a brightening effect, right? But
By what? Just by eclipse?
by eclipse or eclipse is by not brightening but dimming the star, right? But they're also looking for the brightening, right? And there is some object in the halo.
So they looked for the time
Yeah, time
behavior of-
dependence. The time dependence.
corresponding to an unseen object crossing in
Yeah,
front of the,
yeah.
when they see achromatic heat.
Yeah.
But you are saying it's all planets.
No. I'm not saying it's often. It's they see something, but so there is a okay. So if we look at this, stare at this equation again, right? Let's say this is some distance, right? Then there is a degeneracy between mass and distance. So mass over distance is a variable. So mass and distance has some degeneracy. So when they see something, they know that there's something in front, but they can't really have a good resolution on how massive this stuff is and the distance to it. So they see something, right? But the number, let's say if we say the 100% of dark matters are in primordial black holes, then the rate should be much larger than what they see. So that's how they place their constraints on.
But they do not understand where the actual signal is coming from.
They-
But
they
they
know
can say
the-
certainly not from dark matter.
Yeah, they know the line of sight position, but they know the angular position, but they don't know the distance to it.
It could
Everything
be
that's
attributed
closer
to
to-
white dwarfs or brown
Yeah.
dwarfs.
So there are some plausible interpretations.
It could be regular stars.
Yeah. So this is basically saying like if it's 100% dark matter, then they expect to see order 10.
Yeah, but I'm not interested in dark matter.
Okay.
I'm
Yeah,
saying
yeah.
it's interesting in reality. So
Yes.
in reality, they see something,
see
and this
something.
is probably mundane white dwarf.
Yes,
over there.
yes. Or regular astrophysical black holes,
Okay.
or maybe some stars.
Right.
So the difference between again like the angular deflection and the magnification is again like Gaia looks at the whole sky, right? And if you plot this, then there's an interesting relationship. You see. So if we draw how the magnification depends on U, then this is the 1 over U to the 4 plus 1, and then this part is 1 over U, right? So the effect drops off very rapidly, like as you increase the impact parameter. So this is, and if you also draw the angular deflection, then it looks like this. So this is so you can see that the effect decouples much later compared to the brightness effect. So if you're looking for the angular deflection, then you have potentially more event to see compared to just looking for the brightening of the star. But the reason why historically no one has done this before is we didn't have the tool for that back then, but now we have Gaia, and this is a possibility. Yeah. Any questions or comments? Yes.
Yeah, is this effect always safely in the regime that the star is much smaller than the Einstein radius?
Yeah. So.
I assume the answer is yes.
Right.
but
So
I-
let's say this is the parametric dependence, right?
Yeah.
And I believe that Ken last week. So they're talking about Sirius, the radius of Sirius, right? And this is what. 0.6.
6 milliarc seconds, but
Yeah.
Sirius is the biggest.
Sirius
Super
is-
nearby.
Yeah, it's super nearby. Yeah.
Yeah.
So that's at Sirius, the distance of Sirius, then this is larger than the radius of Sirius. Yes.
Fine.
So yeah. So the
Besides, Sirius would not be your lens, right? Because it is visible.
yeah. So
They
it
are
has to
only
be.
doing it for dark objects.
Yes, but the another application is you can also look for, let's say you can look for Sirius lensing something behind Sirius. Then you can measure the mass of Sirius independent of any stellar evolution model. So it is another way to measure stellar mass, because I think all of our current measurement of stellar mass without any binary stars depends on some stellar evolution model. So if you can do this, then that's another way to measure stellar mass.
The actual thing you want to estimate from this is U.
So I will show you later. Yeah. So this is the full picture of gravitational lensing, and next thing is basically what are the signals that we're looking for. So if we look at any stars in the sky, and then plot its location on the sky versus time. Let's say there's a star here, and stars are not static, so they have some velocity. Let's say there's a velocity here in this direction, and what we see on the sky is that it will undergo some circular motion. So let's say we take a snapshot of this star every month, then you will see it undergo this circular motion at a period of 1 year. So this is the parallax effect, and it's basically caused by Earth orbiting the sun, and we're seeing the star at different locations compared to the sun. So if you draw out here is our sun, and Earth is orbiting around the sun, right? And say there's a star here, then we saw this star, and we will see this star in winter at this location, and then we'll see it in this direction, in this location in the summer. Right, so that's explains the circular motion. So Gaia was the mission that they want to measure this, basically how, and you can see that this basically tells you the distance to the star. So a star that's further away, this separation is smaller. So by measuring this, you can measure directly the distance to the star. So that is basically how the distance ladder works. So measuring Hubble depends on actually measuring this. Okay, so see that for every star, Gaia can measure 5 parameters. So you have the 2 locations on the sky, and two velocities, and also basically this distance. So Gaia measured this, and when it do its report the best fit parameters for when they see this motion.
So this distance to the star?
Yeah, distance.
That's from the parallax?
Yeah, that's from the parallax. Yes.
So the star or the lens?
Of the star. So the luminous part of the Gaia sees it emitting light. So yeah, this is this. So the relationship between basically how large this is and the distance is 1 parsec equals to a parallax of 1 arcsecond. So that's basically how we define parsec. This is parallax arcsecond. Okay. So what we want to do then is, suppose there's some lens, let's say, sitting here. Then as the star moves by, then what you will see is this trajectory. Instead of following this motion, it will do something like this, right? So because there's a lens here, so I'm just exaggerating the effect, but effectively what you see is it deviates from this regular motion, and there is some deflection in its location caused by the black hole or lens. So what we want is this, right? So in terms of getting this, what you need is you want the measurements, right? So let's say if you measure this, then you know there's something here, right? So the problem, back to your problem, right? So the reason why we couldn't do this now is Gaia haven't reported this result yet. So all they've done is they give us this, so that it's the best fit parameters.
They don't give you
They
actual
don't give,
positions.
yeah, they don't give you the dots here. Yeah, so it's stored internally.
But they do have them.
They do have them, yes.
So why wouldn't they do what you are planning to do?
Because they're short-staffed, and there's a lot of stuff that need to do in Gaia. So they actually does do something like this that helps. So there was a paper, I think, late last year. So they do see this, and it's for a binary. So this, instead of black hole, is a binary star. So what they see, so the actual discovery process is they found. So Gaia also had the ability to detect this, but it's much worse than all those dedicated surveys. So what they do is they see an anomaly here, and then that prompts the Earth. So that prompts Earth-based telescope to look for this, and they also have, because they have internally this data, so they can determine that this is a binary star, and they solve for the binary order. So they do have the capability of doing this now, but they're just short-staffed on this. Any other questions? Yeah.
So the whole solar system is rotating around the galaxy too.
Yeah.
Is there some sort of parallax effect you can get from that as well, or is that maybe just a harder fit, or what?
You
what
can-
is that?
250 million years.
Yeah, you can estimate that. So I think the period is 4 million years.
Right. Not like a helical pattern. You won't
Yeah,
see that, but you'll see some shift, right?
Oh, you mean like because there's an acceleration, like a centrifugal acceleration.
Right. You're going through. If you're recording the position
Yeah.
over a couple of years,
Yeah.
stars should move, right? Because you're.
Yeah. So if you were thinking about like sun moving in the galaxy and in really short times, then you can just approximate it as a constant velocity. So the constant velocity would be just added.
Right.
So that doesn't affect any.
I see.
I think the precession of the Earth actually is a bigger effect than
Really?
the rotation of the sun. That's
Yeah.
like
So
a compound
the
period.
this X and Y depend on your 0 point on the sky, and then shifts based on Earth's position, precession. So that's why we have. So if you look up any like stellar coordinates, there's always a reference year behind it. So like 2,000 years or like 1950 years. That's big.
The Gaia catalog is quoted in the solar Berry Center. So everything is with respect to the motion of the sun.
I see.
Not galactocentric.
But relevant to this question, they did measure the time rate of change of the stellar aberration to the quasars. So there is a observed acceleration seen because they can see the special relativity aberration effect change very slightly over the mission. So that's been seen at like 5 or 10 seconds.
So yeah, just to basically summarize what Andrea's question was. So currently, Gaia just released its third data release, so that this was in 2022, and they have roughly 1.4 billion stars with these 5 parameters reported. And what we want is DR4, so data release 4, so it's projected to be out in 2025, and it will have roughly 2 billion stars, with all of them have those informations available. So these are all and these are just 5 parameters.
And where is your thesis defense?
If all goes well, it's roughly 2025, yes.
I don't think that's good for you. You don't want to add things
Yeah,
at the
yeah,
last
yeah.
moment.
But they'll almost certainly be delayed.
And how many
It's not-
points per year do they
Good.
have?
Yeah, so this will be a 5-year mission, or 5-year data. So they have total 5-year data, and it ranges from 40 to 200 observations. Depends on the location of the star in the sky.
In 5 years?
Yeah, 5 years.
So it's more than enough for your purpose.
Yeah, yeah. So on average, it's 80 in average. So in our pipeline, for simplicity, we just use 80. But yeah, in reality, it's 40 to 200 depends on.
So sorry to keep asking the
Yeah.
same question again. Wouldn't other people write the same pipeline and exactly on the date of their release they will fire it, or?
Yeah, so that's why we release it first.
But they
So
will?
no one
We made it public.
Yeah. So
Ah, you
everyone
made
can
it
use
public,
it.
okay, so it would be then unfair to do that.
They can do it if they want to.
Open science, baby.
So this, they are re-release?
Yeah.
Because there is time series there, they're not releasing it?
No, they're not releasing there.
I think maybe they did for a few sources. I think they did for like tens of thousands of sources, but probably not enough to be interesting yet.
But why is that? Because why so it?
One suspects there's some calibration problem, because if it was straightforward, then NASA or ESA would make them do it.
What they want to understand their data better?
Well,
or-
except that the agencies don't want them to hang on to it, so they probably have, I would imagine,
And
a
I
year, they have to have
And
some
I think
rationale.
I mean, maybe you know, but some people within Gaia want to use this time series data to discover exoplanets for astrometric wobbles. So they want to hold on to it to do some science of their own.
Usually the agencies don't allow, I mean, there's some sort of negotiation, and the typical thing would be a year. But if
This was
they
agreed
claim
upon
that
before.
there's some
In the original,
subtle features interpreting it that they have to sort out first, I guess.
in the original Gaia contract, they were only going to release the data at the very end of the mission. No intermediate data releases, nothing until the mission is completely over. It's only because of the leadership that's now in place that there's any early data releases. So it's just the opposite. ESA did not insist on any data releases.
Yeah, so
It's very different from NASA.
Yeah, and
ESA
interesting-
is very different from NASA.
and interesting to know that it's 5 years, right? So they already collect all data. They just post processing it.
Hmm.
Yeah.
Are they also looking for lancing? Do they have their own pipeline?
He said they're short
They,
staffed.
they do have something that looks like this, but it's a different trigger, so they have to do their internal, they have an internal alert system. So the internal alert system looks for this first. But Gaia's accuracy for this is not as good as all these other missions, just because of the nature of.
Have you tried to approach them and say, hey, let us join and we'll do this for you?
Yeah, we did, right? Yeah. If you wanna,
Sure. We talked to Anthony Brown, yeah, and he said what Calvin said, that they're short-staffed and that they will probably not perform this.
No, but volunteering to join them and become
Yeah,
part of
once the
Gaia.
data's, yeah, we'll get-
Now. You guys will
I
do
don't,
it for
I
them.
don't, they're not allowed to write papers on data that is not yet public, so.
No, but then it could be made public. Anyway, you didn't
2025.
propose that.
Not
to them.
yet,
You should
no.
consider it.
So is Gaia still taking data now?
Yeah, it is still the, so the nominal mission design was 5 years, but because it's usually telescopes are better designed than what they intend for, so they project to go to 2025, that's the 10-year.
Right, so this is DR4 that's releasing in 2025, that's only the data between 2015 and
Yes.
2020, so there's gonna be a DR, another
Yeah,
DR.
5 years, DR 5, DR 6 for future data.
I see what you said. The problem is if they have a rule, they can't do anything with data that's not totally released, and they want to do other things, even if they were happy for you to join on this, they can't. What a bad setup.
It's a very bad setup, yeah. We should not emulate ESA.
They spend a lot of money.
Calvin, 15 minutes. 15 minutes.
15, okay. Yeah, almost done. So, so our pipeline basically is then we take all the public data available, right? So this gives you these 5 parameters, right? And with this 5 parameter, you can draw out this curve on your own. What we do is you can create a catalog based on this, and you just inject the lens of your interest, and then you could ask what it would look like in terms of the format in here. Then you run your hits to see how many black holes you can see or what the constraints are on dark matter. So to be more concrete, the basic idea is you have a null catalog. So by null, it's just I'm just using the public data available and then just draw out those curves so that there's no source, no black holes that get caught in lens. This is a null catalog, and you can do is you can do add lens here, right? And this gives you a mock catalog. And you run through a method pipeline for both of them, so which basically just contains a 5-parameter fit for fitting this motion, and then an 11-parameter fit for fitting this blue motion. So there's 6 additional parameters from the lens, and you can basically just compare how good or how bad these 2 fits are. Then you can get some sort of test statistics, right? So you have.
What is the usual duration of the lensing event?
Good. So for here, if I draw it like this, then this is really this is a really short event. So this is less than a year, right? So in order for us to detect anything, we need. So if we look at this formula here, right? So we want this deflection to be large and also differ between the mission time. So let's say there's a lens here, but it's not moving as fast as compared to this, then you do not see it.
So what you drew is not typical. The typical thing is throughout 5 years.
Yeah. So the typical thing is if it's slowly moving, then you wouldn't see such a dramatic effect. It would just be like a constant shift in everything. Then you wouldn't see anything, right? So what you want is you can say, okay, what I want is basically this has to change in time dramatically, and let's say if you want this to change by order 1, then the requirement is that this impact parameter here has to be less than the velocity times mission time. So over the mission time, this changes by order the minimum impact parameter, then you will have a large enough impact here to see. Yep. Right. So you want to run both catalog through the pipeline, and you get 2 sets of test statistics. So you can compare those two to say if you want discovery, right? If you want discovery of astrophysical black holes, then you will require some cutoff and test statistic that's larger than what you see in the background. And then for constraining dark matter, you can also just do a comparison here. This will be your signal, and then you will say if I don't see any signal, what's the 90% confidence level on the constraint. So the back to the result. So we said we find in our log catalog we found 4. So the total that we inject is so there are a lot of like galactic models that do simulations on how many black holes there are. So it's usually people do like on the order of 10 to the 8 black holes floating around in the galaxy, right? And of all the black holes that we found in the galaxy, only 1 is not luminous. So most of them are X-ray binary. So you have a black hole, and then you have a companion star, and then sucking some material from the companion star, and then it glows in X-ray because of accretion. So what we want to do, what we would found those 4 would be 4 that has no companion. So they would be like truly like a dark thing. They wouldn't see any like electromagnetic telescope.
What was
You
the
said
mass
there's
range?
one which was-
1. So 1 that's found by Hubble just recently.
But it's found by Ogle and then
Yeah. So yeah, it's found first. Yeah, it's also first found by.
It's for microluminescence.
Yeah, there is also a small like magnitude amplification. Yeah. So
What mass range are you assuming?
yeah. So the mass range we use is roughly 4 to 80 total mass. So yeah. And what we found out of those 4, they're all like pretty close black holes, so less than 500 parsec, and we can actually determine their parameters quite well just using MCMC. So
And when you're doing that, I think maybe you said this, but I missed it. Are you treating each target star independently, or are you looking for the whole field of deflections
we're
from
only
this object?
looking for 1 star for each, because so it's basically here, right? So if you're looking for 1 star, then it's 11 parameter, and if you look for 2 stars, then you add another 5, and things really you get gone out of control really fast.
I see. So
So-
you literally, so then you might find that there's another star in the vicinity
Yes,
that
yes.
also has a deflection, and then you would later be able to join
Yeah.
the deflections.
But that would be
Like a second step.
exponentially harder in terms of like
I see.
computation time.
And how do you treat the sort of observational systematic errors and the uncertainties?
Right.
and
So
on?
Gaia has their projected uncertainty. So for this data format, their projected uncertainty is between 0.01 to 1 arc-second, depends on the brightness of the star.
So you just take it to be
Yeah,
a
just-
statistical thing.
Yeah. So it depends, because Gaia do record its brightness, so we have the expected uncertainty for each stars.
And you're really relying on the angular position and not the brightening,
Yeah, just
because the
angular.
brightening must be much
Yeah,
less
so-
well constrained.
Of those four stars that we found, only one has a brightness that's larger than the Gaia uncertainty. So Gaia has its photometric detector, and it has some uncertainty, and out of those four, only one would trigger, basically one would trigger the Gaia alert system. So all other three they're like the impact parameters are large, that the magnification isn't large enough. And so we found four, and the good news is we didn't see any false positives. So that's basically like a reassuring that our pipeline is not, we're not seeing any like false, just because the sheer amount of stars that are in the catalog, and there's like 1.4 billion. So yeah, that is reassuring. Yeah.
Is there a knob you can turn where you would get some false positives, but you'd catch more black holes?
Yeah, so that's basically the cutoff.
I
right?
see.
Yeah, so you lower the cutoff and you see what it is. Any questions about the black holes?
How are the numbers of black holes you expect to detect scale with mission time? So like with the whole scale mission?
Is it 8 or is it 80? When you go to 10 years.
I believe it should scale that square root of time. Yeah. So currently we're projecting for 5 years, and in the future they will have 10 years data. So it's not really like square root of 2, because like if you have longer time, then you have like I will have better measurement of the parallax, and that's also an additional factor.
Are there, I can imagine that there's binary star contaminants where a very eccentric binary star would look like that.
Yeah, so I glossed over the pipeline. So when I say here we do the 5 and 11 parameter, we also did a 7 parameter. So 7 parameters for acceleration. So basically, if you have a binary star that you
Touch
can,
the screen.
yeah, so if you have a binary, like a wide binary, and the motion could mimic what you would see in like this, instead of like this would be like a long period thing, right?
Yeah.
So we discard those if you can fit it with like a 7 parameter. So that gets rid of any contamination from like wide binary.
I mean, there are very adversarial binary situations, I can imagine.
Yeah. So that's like the best that we can think of. That's not like 2, because for binary star you have 13 parameters. So it's like it gets harder like computationally. So the compromise is to do 7 for the acceleration. And then for compact dark matter, this is the result. So what we do is we just inject an FW profile, and for each mass, the red square is 1.5, and this is the photometric lensing survey that talked about before. So they're sensitive to mass at like smaller masses, and then this is a constraint from a dwarf galaxy, a globular cluster in a dwarf galaxy.
If it was indeed 10 to minus 2, there would be much more black holes than 10 to the power 8. Then wouldn't Hubble have discovered 10 events instead of 1?
So Hubble works a little bit differently, because Hubble.
I understand it's only one measurement.
Yes.
However, here you are talking about a huge, right? It's the same 10 solar masses.
Yeah,
right?
Yeah.
If it is 1% of everything, it's much more than 10 to 8 black holes.
Yes.
Then wouldn't Hubble have discovered more?
Right. So Hubble, the reason why Hubble is because it's not a dedicated telescope for measuring this, right? So if you
But
want,
it did discover
it
it.
does discover.
Okay, suppose it is real. Then wouldn't there be 10 more?
Yeah, so I think this triggered first, right? And then they confirm it with. So because that's a, I think okay.
But
I
still,
mentioned,
the question
Right,
is.
right,
the
right.
question, the
More.
question
yes,
stays.
yes. So they're sensitive to different mass range, right? So they
What was
overlap
the
with-
mass of the Hubble black hole? I thought it was also about 10
It's
solar
really close. It's close to the. I think it's around 7.
masses. 7, 10, that's what I'm saying. It's
Yeah.
the same 10 solar masses. That's
Yeah.
the problem, isn't it?
Um,
Yeah, I don't know. It's
I
just
don't-
for
I
your
don't-
thoughts,
yes,
okay?
it's
You-
the
It will
similar
sit around
constraint.
here, right? So
You're just saying, why isn't that line lower?
oh,
From the
because the
previous
thing is,
observation.
because it's also triggered by Ogle first.
Or is it, I think, so the point here is that you're sensitive to much larger impact parameter events. To get a significant polarimetric magnification, you need to basically, you need to have an impact parameter that's more than the Einstein radius. So that's much rarer than having a large
And
impact
yet
parameter.
they have seen one.
And yet they
Now
have seen one.
you are proposing to increase the number of black holes by a factor of 100.
Because for astrometry, your detectable cross section, if you will,
So it's
for
this-
seeing event is much
it's this
seeing is
plot.
much larger.
Right, so they see only one because it drops off really fast.
Is the question then the other way around? Is it why does the astrophysical black hole only go from 1 to 4 if this is going up by a factor of 100?
Yeah, anyway. We should
Right, so
probably
because
do-
yeah, it's basically because Hubble they still rely on the photometric part, so it still falls off really fast here. But we're sensitive to much larger effect factors. So yeah, so the parametric dependence here is we lose sensitivity for larger mass because they're just less black holes for us to see at larger masses. And for the lower mass part, it's because of this behavior here. So we are seeing, because it drops off as compared to like photometric, you have like a infinite, you can potentially have like infinite magnification, but in terms of angular deflection, there's a maximum. So that cut off at the lower mass end is because you have this behavior here. So that's basically why the microlensing, those surveys look for much smaller clusters. And so the best, basically this is like the best window where astrometric lensing is sensitive to.
In response to Andre's question, I said they're also different of the spatial location. If you assume it's dark matter, it's a much bigger number than astrophysical black holes, but it's throughout the halo. So
Well, they are located differently,
well, it's throughout the dark matter halo. It's not just within the.
but they are not measuring in the dark matter halo. They are measuring by foreground, right?
But you need some star in the background to be lens.
Or you're saying my calculation is wrong. It's not
No,
10
it's not
to
wrong,
8.
but like the number of lenses.
Yeah, I
is
understand.
less than the total number of black holes in the halo. Actually.
Yeah, I understand. That's what you are saying. I cannot translate this into 10 to 10 black holes, which he puts into
yeah.
the. Okay, yeah, I understand.
And that's all I have to say today. So, thank you. Any other questions?
I have a comment. I hope you do
Yes.
find black holes.
That's all we hope, yes.
There should be lots.
There should be a lot.
Can I ask why it's you hit a wall? It's like
Here?
10 solar mass or something. What's that?
Yeah, at around 1 solar mass. So we did do basically what we do is we do a simulation here, but we couldn't find any events. So so the reason is like for small mass lenses, you're limited by this maximum. So once this maximum deflection goes below your sensitivity, then you have no chance of detecting it. Like compared to photometric lensing, you have infinite. You could potentially go like infinitely larger here.
So you can't detect magnification as so much yet for Gaia, but let's say in Gaia 2 or Gaia 100, I don't know.
Yeah.
If you could detect both astrometry and magnification, what could you learn as far as if you would that break any degeneracy?
Yeah, yeah. So the reason why most of them are close by that we discovered in our mock catalog is because it's exactly because of the degeneracy, right? So there is a degeneracy between the mass and the distance for longer distance lens. So, but if the lens is close by, the lens itself will have this motion as well, and that you get great degeneracy with that. So that's why for all the 4 black holes we saw, they're close by, we can like have an accurate understanding of what their mass is. Yes.
Alright, so there's no more questions, then let's thank Galvin. I think I figured it out wrong with the estimator.
Yeah. I was like, this is never gonna take 30 minutes. So.